Then let's look at another case, so-called rotation of green boundary. I have two greens. The green boundary may, in some cases, rotate, which means the green doesn't rotate, but the green boundary tries to rotate. I have two greens. Initially, green boundary look like this, but it may not lay or reside in the so-called low energy green boundary orientation. They may start to rotation of green boundary from this one. The green doesn't change, but the green boundary actually rotates a little bit. It's straight here, end up still and straight, but it rotates a little bit. This is another types of kind of, if you imagine the green boundary motion. And the driving force for this fundamental rotation of green boundary, how do we understand it? Still, let's think a unit boundary length, green boundary length, but unit width. I'm considering this red line. It's actually a green boundary. One green on the top, another green on the bottom. Okay, I'm considering green boundary of length L, but width of what? Unit length, which means let's say it goes into the plane, into the paper by unit length. Okay, and then if this green boundary rotates a little bit, how much? By delta theta. From its initial location, this solid red line, into the new location, this dashed red line. From rotate, green boundary rotates a little bit by how much? Delta theta. Green boundary rotates a little bit by delta theta. Then the free energy change associated with what? With this green boundary rotation. The free energy change associated with this rotation would be, I give it here, delta gamma. Gamma for what? Surface, or in this case, green boundary energy. Delta means the change in green boundary energy would be L times 1. What is L? My length. 1 is my unit width of the green boundary, because if we're talking about green boundary, it's per area. So I have to length times the width gives me area. D gamma over d theta. That is how fast does my green boundary energy change per angle times my actual change in angle, delta theta. Make sense? So this is our relationship from energy point of view. But then, let's say we talk about driving force. If this rotation is driven actually by Fy for the vertical, in this case, force of F, right? Let's say the rotation is actually caused by this force of Fy. And the work done by this force due to this rotation, the equivalent work due to this rotation by this force would be F times what? F times, do you see F times delta Y? The work is actually force times displacement. Displacement is delta Y, as I labeled in this blue arrow here. Force. Okay? And then we say the work should be equal to the change in energy, right? The work should be the same as change in energy, which means F delta Y would be equal to delta gamma, which is L times dy d theta times delta theta. Of course, this one just doesn't show up. Make sense? Left side, F times delta Y is when you consider the energy from a work point of view. What is Fy? The force that drags this green boundary to rotate. What is delta Y? The displacement towards the end that is moving, right? The other side, since we are talking about rotation, we assume one side fixed, the other side moves. Force times displacement would be the change in energy, which is from here. Okay? And then geometrically, Geometrically, what's the relationship between L and delta y? Do you see delta y would be equals this distance? Delta y would be equal to L times what? Geometrically, do you see from here to here, the distance is actually L times delta theta. Okay? So then if we put delta y is L times delta theta, put it here, then if we simplify, we would have the force, the driving force would be in this case similar to Fy would be d gamma over d theta. The driving force for green boundary rotation would just be the differential, the derivative of green boundary energy with respect to that angle. Okay. So fundamentally, this Fy, this driving force for green boundary to rotate, tends to rotate the green boundary towards the one that has the lowest green boundary energy. Okay. Kind of, if we remember the earlier, try to drive them into the so-called cusp position, those locations that you have the lowest green boundary energy. Okay.